In Chapter 34, we're going to study the LC circuit. Now, what is the LC circuit? The LC circuit is nothing more than taking a capacitor and an inductor and connecting them together. So no battery, no electrical grounds, just an L and a C together. We will see that we have established an electronic oscillator that has a direct mathematical equivalent to the block and the spring oscillator that we studied last year, and I'm going to talk more about that in a moment. As far as what is doing the oscillating, in our case for the electronic oscillator, it is going to be the positive charge. So at time t equals 0, we're going to close the switch. The positive charge is going to flow to the other side of the capacitor plate when all of the charge gets over here. The polarity is fully reversed and it is going to oscillate back. So the importance of this circuit is that we now have a way to electronically generate electrical signals, and it has many important applications to radio frequency communications, where the LC circuit can be used to generate radio frequency signals. It can be used to filter those signals, tune the signals to other frequencies, or mix multiple signals together to make a new signal. So many important applications. What we are doing on this first page of notes is not going into deep detail of understanding the physics behind the LC oscillator. We'll do that on our next couple of pages of notes, but we're establishing a mathematical equivalence to the block oscillator to facilitate the discussion on our coming pages of notes. So what we have here is what I hope will be a reminder and remind you of what we did with the block oscillator. So for the block on the spring, we got different frequencies, different types of oscillations, different resonant frequencies, as we're going to start to refer to them, based on this equation, right? Newton's second law, F equals minus kx equals ma equals negative kx d squared x dt squared. Well, if we use our Kirchhoff voltage loop, as it says here, to look at the sum of the voltage sources equals sum of the voltage drops, there's no battery in the circuit, so Q equals CV, V equals Q on C. I took the negative over here and brought it over here in the equation that follows. The voltage that the inductor generates is the Ampere's law, back voltage L di dt, or L d squared Q dt squared. So if we just compare variables, so if we just compare the negative kx to the negative Q on C, we get that the K variable mathematically is like 1 on C. And I will get to explaining why that makes sense. But remember, the stronger the K, the stronger the spring, the faster the oscillation back and forth. So that makes sense. So we're going to see how that equates to having a 1 on C value in the LC circuit. And if we look at the m d squared x dt squared, we're going to compare that to the L d squared q dt squared, and that's how we get the m and the L are equivalent variables. And remember, the larger the mass, the slower the oscillation. And that made sense because it was harder to move that mass back and forth. If it's large, we're going to see the larger the self-inductance value, the slower the oscillation for our electrical oscillator. Well, if we just keep going and recall that the solution to our differential equation above is x equals a cosine omega t plus phi if we had a phase shift. We're not going to deal with the phase shift at the moment. That was a proof by substitution. So if we take the second derivative and plug it back in and plug the x in for x, we saw that it satisfied the equality. And the same thing is true for the block oscillator. So since mathematically we have the same differential equation, we are going to say that Q equals Q max cosine omega t is our solution. So the x variable becomes like the Q variable. So we said the Q was moving back and forth. Here we can think of the block oscillator, the position is moving back and forth, right? We start at position here, it moves to the left, and then moves back to the right. Well, now we're in business. We can very quickly take our derivatives, right, to get the velocity and the acceleration. We can take our derivatives of the q to get the current dq dt, or to get the timed rate of change of the current di dt. And notice di dt is important because I can plug that back in here for the voltage of the inductor, and we'll do that in a moment. So derivative of cosine is opposite sine, to remind you of derivative of sines and cosines. Derivative of sine then is back to cosine. So please pause the video if you have to at any point to make sure all of your annotations are complete. Amplitudes of the functions are given. We have I max in front of the sine function. We have di dt max in front of the di dt cosine function. And the last little bit that we're going to look at is basically what we did to get our frequency expressions. If you recall from the block spring oscillator, omega equals the square root of k on m. Now that was gotten by doing the substitution. So when we substitute the x back in for x, and we substitute the second derivative equation back in for the second derivative, that equality is only satisfied if k equals m omega squared, and that was shown to be experimentally true. So omega equals the square root of k on m, and omega is the oscillating frequency. So the bigger the k, the stronger the spring, the bigger the omega, the faster the oscillator. The smaller the mass that we put on the end of the spring, the bigger the omega value, the faster the oscillator. Well, we do the same thing with our new equations. So if we take our equation for Q here, and we plug it in for Q, and we take our equation for di dt, and we plug it in here, so our di dt equation, and plug it in here, we will see that this equality is only satisfied if omega squared equals 1 on LC, and experimentally that is shown to be true. And again, please make sure you get all of this into your notes. Now we can see why the 1 on C is the same as the stronger spring. Well, if you want a big omega, so if you want a fast oscillator, we need a small inductor, very little back voltage, right? But we also want a small c because of the time constant. We have to go back and think of the motion of the charge q in terms of the time constant. So even though we're ignoring resistance in our circuit, there's always going to be some inherent resistance in a circuit, and whatever value it is, the time constant, right? The faster that capacitor is going to charge and discharge will be based on a smaller C value. The smaller the C is, the smaller the time constant value is. So please make sure that you get this bit here into your notes. That is important to understand why it is that the electronic oscillator, or LC oscillator, operates at a frequency given by the L and the C that we have chosen. So let me pull this down and zoom out, clear all my extra bits here, and let you pause the video here at the very end if you need to make sure your annotations are complete, and we will continue on talking more about qualitatively and physically our understanding of the LC oscillator.